Hi everyone. My name is Yichai. Today we are going to talk about how to simulate micro LED using Crosslight. So this is an optional content for ECE443. Um, so I'm going to talk briefly about the background, the comparison between LCD, OLED, and the micro LED. So LCD are the most major and widespread technology for display. OLEDs are better in some applications like self-emissive and better contrast, and they are kind of popular in modern TV and cell phones and in smartphones displays. Micro LEDs are more robust in terms of longer lifespan, a shorter response time, um, higher operating temperature, and most importantly, it has a lower power consumption. And right now, micro LED is still under development, so the cost for micro LED is still high. But micro LED compared to OLED does not have imprint issues, so that makes micro LEDs as like a future display technology. So in order to simulate a micro LED, we need to consider surface recombination. So typically, because micro LED has a size about like several micrometer, like less than 100 micrometer. So the surface area, the damaged area compared to the entire surface increase. That will deteriorate the IQE, the internal quantum efficiency of micro LED. The smaller the size, the worse the efficiency. So this surface state comes from like a damaged crystal structure at the interface, at the surface, which becomes like a non-radiative recombination centers, and that can capture carriers and recombine the carriers and release its energy in forms of phonon instead of photon. So that will increase the temperature of micro LEDs. Yes. So on the right hand side, you can see that the chip size and the peak external quantum efficiency has this kind of relationship. You can see the peak external quantum efficiency is high when your chip size is about like 100 micrometer. But as long as you decrease the chip size, particularly when the chip size is smaller than 40 or 30 micrometer, you can see like a significant reduction in peak external quantum efficiency. And they are universal for red LED, green LED, or blue LEDs. So we need to use simulation to study what's going on and how to design our LEDs to have higher performances. Okay. Yeah. So scaling down on micro LEDs enhance surface effects due to increase the surface area to bulk volume ratio. At the end, I'm going to talk about the simulation details. So the most important things compared to regular LED simulation is that we need to add a surface recombination in a solver file. So we need to first search what are the surface recombination parameters you want to simulate. So this project was demonstrated by the other TA, Yuche. He used this set of surface recombination parameters I found in this textbook. So the surface recombination velocity is 5 times 10 to the 4, and surface trap level is about 1.4 electron volt below the conduction band. And the surface trap density is 10 to the 10 per cube centimeter. and the surface carrier lifetime is 1 microsecond. So we need to use this interface argument in the solution file to enable surface recombination. So this is the device structure. So this device structure is like an N-type gallium nitride with a doping concentration of 10 to 18, 2 micrometer thick. And then on top of it is 2 quantum well indium gallium nitride sandwiched by gallium nitride barriers. So the indium mole fraction here is 0.194. So this is designed for blue LED. On top of it, we have P-type gallium nitride with a acceptor level, acceptor concentration of 10 to 17, 50 nanometer. And on top of that, we have a contact layer of a heavily p-doped gallium nitride with an acceptor concentration of 10 to 19. And the thickness of this layer is 50 nanometer. And because this is like a 2D simulation, we need to change this L. L is the size of this micro LED. So we need to change this, treat this L as a variable, and we change it from like 500 micrometer, 200, 150, 20, 10, 5 to down to 2 micrometer. And the typical size, typical LED size has a L of 300 micrometer. And for the next generation 4K and 8K displays, pixel pitch is around 30 micrometers. So this range of L covers the typical LED structure and the micro LED structure. Okay. Yeah, and then we're going to perform the simulation by activating surface recombination and deactivating the surface recombination and see how does this surface recombination play its roles in efficiency degradation. But most important of all is that although we are simulating gallium nitride in this case, we assume that there is no polarization in this device, meaning that we are growing gallium nitride on the nonpolar plane. So they don't have like polarization induced the sheet charges at the interface. So if you are like you are experienced more of like gallium nitride or nitride materials, probably you will have this question like why is the under like flat band conditions, why is like a equilibrium condition, I don't have like a polarization induced the sheet charges. No, because we are not including that effect in this simulation. Okay, so first we need to generate the first layer of gallium nitride on this layer, 2 micrometer, and with undoping of 10 to 18. And because we have 2 columns here, this is the first column, this is the second column. So we need to define the material and the thickness separately. So here we define 2 columns, and here the width is actually the variable. Here we use 2 micrometer. Of course, if you want to simulate different L size, then you need to change this W for these 2 columns. Okay, and for the first layer, first column, we have gallium nitride 10 to the 18 doping concentration per cube centimeter. Yes, and we have a thickness of 2 micron, and then we add indium gallium nitride quantum well, gallium nitride barrier. I'm going to define this InGaN.QW and the GaN.bar later separately. And I'm going to add one more quantum well. And then on top of it, we have p-doping gallium nitride with 50 nanometer thickness. And the doping concentration is 10 to the 17 per cube centimeter. And on top of this layer is gallium nitride. Oh, by the way, I have to say that because here you have 2 layers, right? So if you want to define the second layer, the second column of this layer, you need to define the P-GaN in the first column, but on the right-hand side, you need to define this layer as void. So you can see that you have void in the second column. Okay. And then finally, on top of it, we have heavily p-doped gallium nitride layer with a doping concentration of 10 to the 19 per cube centimeter. Yeah, and the thickness is 50 nanometer for this layer. And then we add the top contact onto it because we define the top contact to be the thickness from 0 to 0.5 L. And because our L is 2 micrometer defined earlier, so you can see my first column is thickness is from 0 to 1, which is 1 micron. And for my second column, I specify the contact thickness from the position from 1 micron to 2 micron, which means that it's starting here 1 micron to 2 micron. Yep. Yeah, and then this is the file, .layer file. And then we need to generate a separate QW file. So in the quantum well region, we define our quantum well material, indium gallium nitride, with a mole fraction of 0.194, and we need to specify it as like a quantum well model. And we need to define the material for the second column, which is void. And the quantum well thickness here is 5 nanometer. Okay. Yeah, I think this is really straightforward. And then we need to generate a barrier file. Here, the barrier file is gallium nitride, and for the second layer, a second column, we define it as void material and the thickness of this barrier region, this gallium nitride barrier is 5 nanometer as well. And in a solution file, you need to load the mesh information. I need to set your output file, and you need to allow the output of quantum information, and then you input the doping profile, the material profile, and then you use independent multiple quantum well module and the quantum transport module for multiple quantum well to simulate the carrier transport physics in the active region. Okay, and then here I specify the Auger coefficients for the material equal to 2, and in this case the material index equals to 2 implies the indium gallium nitride, which is our quantum well material. So we define Auger coefficients for EEH process to be 3 times 10 to the minus 30 centimeter to the power of 6 divided by per second. And we define the same Auger coefficients for HHE Auger process for the quantum well region. And then we define the B coefficient, which is radiative recombination for this indium gallium nitride as well. And this B coefficient is 6.65 times 10 to the minus 10. Okay. Okay. And in the first part, we need to define its interface recombination parameters. We need to provide first the surface trap information, and second, define the surface recombination velocity information. So first, we specify this trap to be like a acceptor type, and we define the surface region within from 0 to 1, and in Y region, in Y direction from 0 to 3 micron. Yes, and we provide the surface trap density, the trap level referenced to the top of the conduction band, or the bottom of the conduction band. And then we provide a trap lifetime of minority electrons and minority holes to like 10 to the minus 6 seconds for electron and hole. Yeah. And third, this syntax, this argument, surf trap number equals to 1 implies that this is just a label used to identify a specific kind of trap. Okay. And once we define the surface trap information, then we need to define surface trap recombination velocity. Here we specify the same region to enable surface recombination. Okay. And we first provide the surface recombination velocity for electrons and also for holes. They are having the same value. And this outer recombination only argument means that only the triangular edge exposed to the outer surface count as like a surface region. So this correction eliminates the like a corner effect. So you can see on the right hand side and compare the surface on the left hand side and the right hand side. So here we are going to consider this case. We only consider the surface exposed outside of the LED. Okay. Okay, and then we specified the Newton parameters. You can follow this default value unless you have any convergence issue. Yeah, and we can talk about that if you have any convergence issue. Then similar to regular LED simulation, we need to set our initial wavelength. And we know that this is for blue LED. So the wavelength range should be around like 350 micrometer, 350 nanometer to 550 nanometer. And the initial wavelength is in between this value. So we set like 0.45, which is equivalent to 450 nanometer emission. And this PRN.GAN number is the number of points sampled within this wavelength range. So the higher, the better, the more accurate the results. Okay, so if you want to extract like a peak emission wavelength, and you need to set this number to be much higher so that you can get more accurate results. Okay, and LED simple is like a bundled algorithm for you to simulate LED. And you set the initial wavelength to be like 0.45 micrometer and spectral number 300. Photon recycle, no. This is the default value, so you don't consider like photon recycling, meaning that if you have like a photon generated from one quantum well, and that photon is going to be reabsorbed by the other quantum well, and we are not considering that effect because our quantum well have roughly the same properties, same ground state. So if you have like a very different quantum well geometry, for example, in one quantum well you are in the Moore fraction, one is deeper, you have deeper quantum well, and you have shallower quantum well, then you are going to consider photon recycling effects. Okay. First, we solve the self-consistent equations under equilibrium conditions, and under this condition, we are not biasing our device, and this is a good initial conditions for us to before ramping up our voltage. Okay, and then once we obtain a good initial gas, then we ramp up our voltage from 0 volt to 10 volts, and and we switch the bias voltage at the P contact from 0 to 10 volts with an initial voltage step of 0.01 volts and a minimum step of 0.01. But the voltage sweep stops when the current density, this current 2, goes above 0.01 plus minus 0.005 defined by this auto within. Okay, so this argument is going to ramp up, it's going to simulate the results under low injection. And once this simulation is completed, then we consider high injection case. So here in the second line here, we switch the current density at the N contact because we specify current 1. This means the current density at N contact from the pre-converged value to minus 50 amp per meter. So this is the default unit for this value. And because we are collecting the current density at the N contact, so minus implies negative value implies forward bias. Yeah, and we, with an initial step of 1 milliamp per meter, here defined here, and a minimum step of 10 to the minus 6 amp per meter, and a maximum step of 2 amp per meter. Yes. Yeah, and this is the result of, wait. Okay, so this is the result. This figure shows the size of L as a function of internal quantum efficiency. Yes, and this is the measurement of the peak IQE. And the peak IQE actually is a function of current density, but you can extract it for individual size. So the peak IQE achieved for each size is seen in the figure. So down to like 50 micrometer, the reduction is not significant if your size is above like 50 micrometer. But the IQE reduces significantly if you decrease your micro LED size from 50 micrometer to down to like 2 micrometer. You can see the significant reduction in terms of peak IQE from like 70% to only 20% at the 2 micrometer. So for micro LEDs with significant surface effects, it's better to make the mesa size only as small as necessary. It doesn't mean that you need to have really small size, because you can decrease the size, which increase the resolution, but at the same time you are decreasing the peak internal quantum efficiency at the same time. So there's a design trade-off for you to do if you want to simulate micro LED as your final project. Yeah. And the second result is to show the current density as a function of internal quantum efficiency for different mesa size, different micro LED size. So at a larger size, the IQE reduction is not significant. For example, like 500 micrometer, 200 micrometer, and 100 micrometer. You can see their peak IQE is about like 70 to 75%. But as long as you keep decreasing the size down to like below 50 micrometer, you can see the significant reduction in the peak IQE. You see, every time when you decrease it by half, roughly by half, your peak IQE decreased by about 10%. Yes. And this result shows the current density as a function of peak as a function of IQE. This does not consider, okay, so this result considers surface effects, but this result does not consider surface effect, surface recombination. So you can see that the peak IQE actually is not affected by size right now because we are not considering surface recombination. Then the onset of peak IQE is sooner at smaller size. So the smaller the sizes, the higher the larger the current density is, and it's defined by amp per meter square. And because here the current density defined by inside the CrossLight is amp per meter. If you want to calculate the current density that we typically used, you need to divide this value by the contact width. Yeah, so in this case, you need to divide the current density by the size of your LED. Yeah, and the efficiency group is increased with smaller size. Yeah, so efficiency group means that the reduction of the efficiency compared to its maximum value. So you can see that smaller size in micro LED typically lead to higher, stronger efficiency group. And I think that's for micro LED simulations. We did not talk about how to plot those data because I assume that you know how to collect those data from like a regular lectures. You use PLT file or you use CrossLight view to extract the IV curve and then collect the peak IQE so that you can plot this kind of data. Yeah, you need to have like post-processing technique to plot this data either using Origin Lab or using Excel. Yeah. Thank you very much.